Welcome back. In the last video, we went through a few of my favorite resources. Now, this is definitely not an exhaustive list to find machine learning research papers and code, but here are 4 pretty great resources, and you'll definitely find more as you go through your machine learning journey. But let's now make it concrete of what we're doing. We've kind of hinted at this, or we've said it a few times now, but we're going to be replicating the Vision Transformer paper, or the VIT paper, with PyTorch code. And so here's the paper we've been talking about. An image is worth 16 by 16 words. Transformers, which transformer is becoming very popular and very effective type of neural network architecture for image recognition at scale. So this is the paper that originally brought in the transformer architecture for vision. Previously, prior to this paper, the transformer had been used mostly for NLP, or natural language processing problems, or problems dealing with text. So if you recall way back to, I think it was section 2 maybe, or section 1, I can't recall, but right back at the start of the course, we said there's some machine learning versus deep learning common algorithms, and we talked about the machine learning algorithms as typically being the best for structured data, and the shallow algorithms, that is, because the deeper learning algorithms are better on unstructured data. So this is like tables with rows and columns, whereas this is like audio and images and video. The more layers, the more chances you have to learn a representation of your unstructured data. So we did say, I did say that what we're focused on building with PyTorch was neural networks, fully connected neural networks, convolutional neural networks, and I kind of skipped out on the transformer, but I decided as I started making the rest of the materials, the transformer is getting too popular and too well-performing not to cover it. So we're covering a transformer, and not this kind of transformer, this kind of transformer, a vision transformer. So a transformer architecture is a convolutional neural network, uses convolutional layers for its main learning algorithm, whereas a transformer is generally defined as an architecture that uses multi-head attention or self-attention as its main learning mechanism. And if you'd like to read more about a transformer, you can read the paper, Attention is All You Need, or What is Attention in Machine Learning, or J. Alamar, Attention, there we go. These are all great resources. What is attention? Attention, what is attention? Attention mechanism, attention. Attention is all you need. This is the technical paper that you can read through that introduced the original transformer, but for text. A whole bunch of resources here for learning attention, and the illustrated transformer. So this is a great visual overview of what a transformer model is created with, but we're not going to be really focused on going through the technical details. Well, we are going to be getting technical, but we're going to be focused on writing code rather than talking about overviews. So look at all this. This is a beautiful blog post. That's your extra curriculum. Alongside reading this paper, I'd highly recommend reading this blog post. You might not get many things the first few times you read them. I've read this paper probably half a dozen times now, and I still pick up on something new. But we're going to be focused on writing code so you can see what happens when we build a paper with code. So let's jump back in. That's what we're doing. We've got the vision transformer. We want to turn this into usable PyTorch code. And so specifically, we're going to take the vision transformer architecture and we're going to try it out on our food vision mini problem. So that's the project we've been working on throughout the last few sections, taking images of steak, sushi, and pizza, passing it through a computer vision neural network. Previously, we've been using convolutional neural networks and getting good results, and then we have some sort of classification output here. But we want to see, if we were a machine learning engineer, let's just pretend we are, and we want to get skills. Well, one of the ways to get skills would be to take the latest and greatest computer vision architecture published by Google Brain Research team and try it on our own problem. In fact, maybe that would be a challenge that would be set if we were at a machine learning engineering role. It's like, hey, this new computer vision architecture came out a week ago. Can you implement that for the food vision problem? Well, let's give it a shot, hey? And so we've got our inputs. Now, this is a neural network, very customizable. We're going to be substituting in the vision transformer architecture. So this is the original VIT architecture, Vision Transformer. But if we turn it into Food Vision Mini style, we might have something like this. We have an image of pizza. We break it up into patches. We'll see what this looks like later on. And then we feed those patches, or we embed them first and pass them through a transformer encoder layer, which is this, multiple times, a few layers here. We're going to go through this step by step, don't you worry. And then we pass the output of that to an MLP head. MLP stands for multi-layer perceptron, if you wanted to find out what that means. Multi-layer perceptron. As I said, there's going to be a lot of stuff here that I'm kind of just going to throw at you, but trust me, we can learn this all together. If you don't understand something, pause the video, search it up, read it, come back. If in doubt, run the code. So a multi-layer perceptron is a fully connected class of feed-forward artificial neural networks. So that's just the neural networks that we've been building. The term MLP is used ambiguously. Yeah, this is a little bit confusing. Sometimes loosely to mean any feed-forward artificial neural network. So in the case of the Vision Transformer paper, an MLP is a layer with, well, we can just search this up, right? Have a look at this. MLP, MLP, MLP. There we go. The MLP contains 2 layers with a Gelu nonlinearity. What the hell does that mean? Well, this is where we could get stuck on a little bit of a treasure trail. We can go Gelu nonlinearity. What is that? Gelu explained, papers with code. We could read that. We're not going to do that now, but just know that a multi-layer perceptron is some kind of neural network with a given number of layers. It could be any amount, but usually it refers to maybe 1 or 2 hidden layers. So yeah, I refer to as vanilla neural networks, especially when they have a single hidden layer. So a lot of things going on, but nothing we can't understand if we break it down step by step. And finally, let's finish off with what we're going to cover broadly. So we're going to get set up. That's how we'll start our code. We've written a whole bunch of reusable code in previous sections. So rather than rewrite that, we're just going to import it and run it. We're going to introduce machine learning research paper replicating with PyTorch. So we've kind of talked about that in a high level overview. Now it's time to start writing code. We're going to be replicating VIT, the Vision Transformer, for our Food Vision Mini problem. This is so exciting, taking state-of-the-art research, building it ourselves for our own custom problem. We're going to train our own custom VIT, and then later on, we're going to see if we train a VIT from scratch, so with our own custom data, does that perform as well as doing feature extraction with a pre-trained VIT or Vision Transformer? Now, this is transfer learning, right? Like what we covered in section 6. And how are we going to do it? Well, like we always do it. We're going to be cooking up lots of code. Just like a chef might go to a recipe and replicate it into an edible dish, we're going to, as machine learning engineers, go to this beautiful machine learning research paper and treat it as a recipe that we're going to turn into some usable code. So with that being said, let's code. I'll see you in Google Colab.